Okay, so you know we've been talking about work, right?
Yeah.
That's sort of been our main focus. So work is actually directly related to energy. Do you guys remember learning about kinetic energy back in physical science at all?
Mm-hmm.
Yeah, okay, so what is kinetic energy?
Movement.
Yeah, all of you guys who said that are right. It's the energy of something that's in motion. It has to be in motion if it's going to have kinetic energy. So if something is still, does it have kinetic energy? No. Does my thing of water have kinetic energy? No, it's still. There's no kinetic energy in there, okay? So what happens is when you do work on an object, you change its energy. Okay? Work on an object is the same as change in energy. So who in here likes to be the one who pushes the shopping cart in your family? Really? That was like always my favorite thing. Me and my dad would have to fight for it. Okay? I still push it now that I'm married. I insist on being the cart pusher. I just love it. It's fun. Okay? So when you first get out of the cart and you're just standing there with it, does it have any kinetic energy? What about when you start to push it? Yes. Are you doing work on that cart as you push it? Yes. Why? How do you know that you're doing work on it?
Because you have to move it. Yeah.
Yeah, you're applying a force and it's moving a distance, okay? So that means you're applying work when you move the cart. So let's talk about that then. Now, if we are moving a cart, what forces are acting on it?
Force applied. Yeah. Maybe some normal. That's about it.
Okay? That's pretty much all I have. We'll act like there's no friction, all right? We're going to ignore friction. We're going to say, you know what, we don't care about you today, friction, all right? Now, if I asked you to find the force, like the overall force, what would my equation be? The F equals what? MA, okay? Now, what if I said I want you to find the acceleration? How would you rearrange this?
F over M equals A.
Yeah, F over M equals A. Okay, so that's really cool. Now let's keep thinking about the cart, all right? And we're thinking about it all in terms of previous knowledge. So we have this cart, we're pushing it. There's some acceleration, it's moving some distance, and it has some velocity since we're pushing it, right? So if we have all three of those, we learned some equations that start with a K that use all of those. What were they called? Kinematic equations. Okay, so let's think about this kinematic equation then that has all of that. We had Vf squared equals V naught squared plus 2A delta x, okay? And delta x is a distance, right? Yeah, so that's sort of like the same thing as the D that we have in work equals force times distance, right? That's basically the same thing as delta x. Okay, cool. Now, what do I need to move if I want to get this whole term by itself?
Subtract the V naught.
Okay, good. So we're going to have 2A delta x equals Vf squared minus V naught squared. Okay, now is when we're proving right now, okay? We are proving that work is related directly to energy, all right? So keep yourself strapped in for this. This A right here. What did we just find the A equals? Okay, so what I'm going to do is I'm going to say 2F over M delta X equals Vf squared minus V naught squared. Okay, so all I did was I took this thing that we found for A and I plugged it in for A here. So you see how it's the same thing? Nothing's really changed? Okay, now something that I want to point out, do you see work anywhere in here? The equation for work? You see the equation for work? Yeah, so I want to know, what do we move around to get what I've circled by itself? So let's start baby steps. What would we do with the 2? We divide the whole thing by 2, right? Okay. So if we divide the whole thing by 2, we would have F over M delta X equals VF squared divided by 2 minus V naught squared divided by 2. Because when you divide the whole thing by 2, isn't it the same as writing this? Yeah, okay. Now what's the last thing we need to move? Yeah, multiply by the M, right? So we're going to take this M, and when we multiply by the M, we get that F delta X equals, remember that M would get distributed, right, if we multiply by both sides? So it's going to be M VF squared over 2 minus M V naught squared over 2. Okay? And the way you're going to want to write this, because it makes more sense personally in my mind, is that F delta X is equal to, I just like to pull out that 1/2. 1/2 M VF squared minus 1/2 M V naught squared. I don't know why, but this makes more sense in my brain. Does that make more sense to anybody else in their head? Yeah, it's a lot easier to look at, right? Okay, so I want to tell you what you just derived. You just derived that work is equal to the change in kinetic energy. Okay? That's what that means. Work is equal to the change in kinetic energy. Which means that at the end of the day, what do you think is our base equation for kinetic energy? This is final minus initial right now. This is like final kinetic energy minus initial kinetic energy. What do you think it is just for kinetic energy? Yeah, it's just going to be 1/2 mv squared. That is our equation for kinetic energy. This is the equation for the change in kinetic energy. Since you guys remember that change in is always going to be our final minus our initial, right? Okay, so here it is because you have a final and you have an initial. Here it's just a V at a certain point in time, just one point. Okay, and I've got some good news for you guys. You know how when we were doing work, we had another equation that we added on cosine theta to get with an angle? This is still the same even if there's an angle. You don't have to incorporate the angle. Very nice, right? Okay, so, and all of that stuff that we just did to derive the equation, I'm not going to make you guys remember how to derive it, okay? I just wanted to show you where it comes from and how work and energy are connected to each other. One other thing, though, before we start doing some examples together, what do you think the unit of kinetic energy is?
Meters.
It's still going to be joules. It's still joules. Praise the Lord, right? Still joules. Okay. So, who in here has ever had somebody run into them? Like, just slam into you and it's horrible. Okay. I want you to imagine that situation in your head, okay? And this person who's running into you is going to have a mass of, let's say, 62 grams. I mean kilograms, sorry, they're not that tiny. That would be like, whew, super tiny person. All right. And then they have a speed or a velocity of 2.5 meters per second. I want you to tell me what their kinetic energy was when they were running into you. What was their kinetic energy? When you think you got an answer, just yell it out.
Is it 193.75?
You say 0.75? What are the units? Maybe that's the answer. We're going to see if anybody else gets it, though. I hope it's right, too. Yeah, you agree, Gwen? I saw the nod. Anybody else agree? You agree, Anna? Okay, cool.
I agree.
You know what? I agree too. I think this is the right answer. I think this is beautiful. Now, if you're wondering how the heck did she get there, she said that kinetic energy is 1/2 mass times the velocity squared. Okay, that's how we got there. Just if you're wondering, all right? So let's think about this again. This time we're going to have a truck. Now, I don't know if this is accurate with the mass that I have here, but let's just say it's one of those like 18-wheelers, okay? And it has a mass of 3,900 kilograms. So it's only a little bit larger than the person who ran into you. Okay, just a little bit, right? Not very much. Now, it is moving forward at a velocity of 6 meters per second. And we want to know, what is the kinetic energy of this car? Find it for me. What is it? Okay, awesome. Now tell me, what would it be if it was moving at a velocity of 12 meters per second? 200 what? What are the units? Awesome, I agree with that too. Now, I've got a question for you. Would you like to be hit by the semi when it's going 6 meters per second or 12? Not at all wasn't an option.
Well, probably the first one.
See, personally, I want to be hit at it going faster. Just for the pure facts that then maybe I'll just die. Here, I have a chance of slipping into a vegetative state or like being paralyzed and all sorts of crazy things. Or dying like a slow, painful death. Maybe here it can be like slightly instantaneous, right? Who knows? Guys, it was a joke. Come on. It wasn't a bad joke. It was a good joke. Okay. Let's see here now. Okay, we've got a small boat. Let's say maybe it's like a fishing boat, okay? So we're going fishing. And it has a kinetic energy of 15,000 joules as it's moving along, okay? Now, as it's moving, it's going at a velocity of 5 meters per second. I want you guys to tell me, what's its mass? Oh, I heard that. Do we want to try and rearrange this one together? I heard yes and no. Show me if it's yes. You know what? You guys try it first, and if you need me to, I'll help you out. Okay, what did you find, Trunks?
1,200 kilograms.
Okay, I'll put it up as one of the answers, all right? Yeah, he said he got 1,200 kilograms. I don't know if that's right or not, though. I'm not going to say. What'd you get? You got 100 kilograms? You got 120? Okay. You got a what?
77.45. I don't know.
We got a 77.45. Okay, I think this is the part in the show where I say let's do this together. Because we got all sorts of different answers up here, right? They're all over the place. So, if we're solving for mass, what's the first thing we should move? Yep, we're going to multiply by 2. So I'm going to say 2KE equals MV squared. Okay, now what do I do?
Take the square root.
I'm not going to take a square root of anything. Yeah, you take that V squared and you divide by it.
I got it.
And then you multiply, like, you just type in.
Now, we're going to have 2 times 15,000 divided by 5 squared. So you guys enter that and tell me what you get.
Oh, no, chunks are right.
It's what? You said 1,200?
Yeah.
All right, so do we all agree that Trunk's answer at the beginning, like 0.5 seconds in, was right?
Yeah.
Yeah, all right, awesome. Any questions about that one? No? Okay.
Don't erase it.
Okay, yes, ma'am.
I'm still right. I forgot to type the 0.
Okay, while Rose keeps writing, I want to ask you guys, if I've had you find kinetic energy and I've had you find mass, what do you think I'm going to want you to find next?
Velocity.
Oh, you're all so smart. All right. So let's see here. Can I erase it now?
Yeah.
Awesome. All right, so let's look at this next scenario. For this one, we've got a baseball. So please keep in mind that your answers should be not too big, because who can throw a baseball super, super fast? Not me. Okay, so we want to know, what is the speed of a baseball that has a mass of 0.15 kilograms that has a kinetic energy of 77 joules? What is its mass? All right, you guys go ahead and try by yourself first. Huh? Velocity, yeah. Velocity and speed are interchangeable, yeah. What did you get? Okay, so we've got one guess. Okay, we've got Aaron and Trunks have it. I'm just putting a check to say that somebody's agreed with it. That's the only reason there's a check there. Does anybody else have a guess? You agree with that one too?
Mm-hmm. What'd you say?
32.04. You agree? Did you really get that?
I really did love
it.
I can't see that, but I see that you actually typed stuff in. Okay. Do I need to show how we got here? I heard a yes in there, so I'm going to go ahead and do it, okay? So, kinetic energy is equal to 1/2 mv squared. What do I want to move first to get the v alone?
The 2.
The 2, okay. So we've got 2 ke equals mv squared. Now what?
Divide by the m.
Divide by the m, and then finally?
Take the square root.
Take the square root. Good. So we're going to have square root of 2 times 77 joules divided by 0.15 kilograms. And that gives us what?
32.04.
32.04 meters per second. Meters per second.
So eventually, should we like get a certain amount of joules, like for the truck storing 50,000 joules? Can we turn that into miles per hour eventually?
Yes, you can actually.
I'll let her leave.
I think we do an example later on where I tell you like the equivalence to miles per hour. Okay, any questions about this one? I'm slowly erasing it until somebody yells at me, then I'll do it. I think that was a sarcastic stop. Okay, so now I want to bring back to our attention what we said earlier, what we derived, which was that work is equal to that change in kinetic energy, which is equal to 1/2 mvf squared minus 1/2 mv naught squared, okay? I'm putting these semicolons here to just separate stuff. They don't stand for anything. I didn't put J's. All right, so let's say we want to know how much work is required for a 74 kilogram sprinter. 74 kilogram sprinter to accelerate from an initial velocity of rest, which is how many meters per second? 0, because you're at rest. So to accelerate from rest to 2.2 meters per second. All right, what we were asked is how much work? Remember that the best thing to do is to figure out if something equals 0 first and get rid of it.
Why, thanks.
Okay.
The 179.08.
That's what I agree with that too. 179.08. Yep. Yeah, Nala got it too. I'm talking about
Don't worry, we'll back it up and go over it together, okay? Yes, Aaron? Huh?
Yeah, you can
Just subtract the velocity.
I mean, you don't know.
You
Yeah, you don't put in the thing on.
I think it's.
All right, so let's talk about how we did this, okay? We said the work is equal to 1/2 mvf squared minus 1/2 mv naught squared. Out of these three terms, which one's 0?
V naught, second one,
Yeah, that goes to 0.
and then you plug it in.
So now we have the W equals 1/2 mvf squared. Do we have to rearrange anything to find the work?
No.
All right, so we're going to plug in 1/2 times 74 kilograms times 2.2 meters per second squared. And what do we get?
179.08 joules. Look, I kind of got that right by accident. I did not see the subtraction with the. You didn't see it? No, I just tracked it out. I got it right. Because, usually the numbers are 0
Huh? Do you need to be closer?
I'm going Monday to get my eyes.
Okay.
It's just mostly the
No, I really am blind though. I choose not to blind my car. I got eye surgery.
Oh my God, eye surgery
It
too.
runs in the family.
Yeah. Everyone in my family wears glasses.
He got laser eye surgery.
No, it's very risky.
Is this okay?
Yes, go ahead.
I got it on.
All right, we're moving on to another example. We are trying to lift a box off the ground. The mass of the box is 4.1 kilograms, okay? It is starting at, what do you think? 0. Okay, because it's starting from rest because it's on the ground. We are going to apply a force of 52.7 newtons to try and get this baby moving. And overall, it will travel a distance of 1.6 meters. Okay? We want to know 3 things. The first thing we want to know is the work that we did. So the work of the applied force, we want to know what that is. So that's A. For part B, we want to know the work that was done by gravity on this box. And then for part C, we want to know the final velocity of this box.
Okay.
So let's start at A and work our way down, okay? All right, work of the applied force for part A. How do you think we'll solve for that? Force times distance. What's our force? What's our distance? Okay, so what is the work of the applied force? Let me make sure I agree with you. I do, okay. What are the units? Okay, perfect. We got part A done. Part B, the work due to gravity. Well, there's a few things to think about here. One, you notice how the work that we did is positive, right? That's because our force is up and the box is moving. Up. Now, which way does the force of gravity act? But what way is the box moving? So would this be positive, negative, or zero force? Zero work. It's going to be negative. Okay, so we're going to put the negative so we know. So, how are we going to solve for this? What's the force due to gravity? That's the acceleration due to gravity. What's the force due to gravity? How do we find it?
9.8 times the mass of the object.
Yeah, so we're going to take the mass of the object, which is 4.1 kilograms, and we're going to multiply by 9.8 meters per second squared. Because remember, we already put that negative on the outside because that's the deciding factor, is that we know that the work is negative. Now, that takes care of the force. How do we find the work? It's force times what?
Oh, then times by the distance.
Yeah, then we need to times by the distance, which is? Yeah, so what is going to be our work due to gravity? Negative 64 point what?
29.
Thank you. What are the units? Joules. Okay, cool. We're done with part B. Okay, now I've got part C. So we need to know the final velocity. So do you think we'll need to use equation 1, 2, or 3?
Oh,
1, okay. So this total work that's done is going to be equal to the change in kinetic energy. Are any of those terms 0? Yeah, that's going to go to 0. Okay, so now we have that work is equal to 1/2 mvf squared. How do we rearrange to solve for VF? What do we need to do? Okay, so we're going to have 2 times work equals equals mv squared. I keep on writing everything wrong. No. Okay, what do we do now? Divide by m, so we have 2 times work divided by mass equals VF squared. What's the last thing you got to do? Take the square root. Okay, now here comes the hard question though. What's the work? We do what, Trunks?
Subtract A from B. So the 84.33.
That does make sense though.
For work, what do we do to find total work done by something? We do what? Add them together, okay. If we're adding them together, we're going to do 84.32 plus negative 64.29. What's that going to give us as our work? Hold on, hon.
That makes sense, yeah.
And what's the mass?
1.4. Oh, no, 4.1 kilograms.
All right, well, you guys do that. I'm going to explain where the work came from, okay? If you ask me where the 20.03 came from, please pay attention right now. So this work right here that we're doing, this is a total work done on the object. So we talked about last week how to find the total work done on an object. You take the works and you add them together. You sum the works. So what we did to find this work was we took the work of the applied force plus the work of the gravity. So we said that overall work is 84.32 joules minus 64.29 joules, since it's negative, and got an answer of 20.03 joules as the overall work done on the object. Now, does anybody have the final velocity? What is it?
3.13.
What are the units?
Meters per second.
Does everybody agree with that?
Yes.
That is right. Good job. No, you're not done for the day.
This has conflict.
Yeah, but who does that?
But
I didn't do it over the weekend. I did it Friday.
well, what's going to throw it off? You can just tell.
All right. I'll leave this up here for right now, since a few of you guys I still think are getting down part C. Or is parts A and B, though.
I need a new notebook.
And, oh, if you need a new notebook, I have a suggestion. I have
Oh, not for
these.
your class, I'm talking for AP.
Oh, well, either way, these are great. You can order a pack of 6 from them from Costco for like $30, and they're moleskins. So they're the nice stuff. Huh? No, this is the brand name.
Oh, I thought you were talking about they were moleskin. Like,
No, the name of the brand is Moleskine. They're like the best journals out there. Okay, I'm gonna give you guys one to try and figure out on your own. Now you're gonna have to think about this, okay? So, at the beginning, we know that, let me tell you, Drew, we're dealing with an object that's falling, okay? The object has a mass of 0.4 kilograms. All right? Now, at the beginning, it's falling with an initial speed of 6 meters per second. And then later on, it has a kinetic energy. Oh, I didn't put a J, that's the units. It has a kinetic energy of 25 joules. So you guys are thinking about like this, like initial, and then this as a final, okay? Now, what else do we know? Well, nothing. We want to know, what is the kinetic energy initially? That's part A. For part B, we want to know, we're at this final thing, what its velocity is. And then we want to know overall how much work was done. So I'm going to give you guys some helpful hints on how to go through this. And yes, you are allowed to work with a friend. You need to look at this as this is all initial. So I'll even put KE naught. This would be like a KE final. And these are all finals. This right here is going to be a total. And this is the mass for both scenarios. Get with a friend and try to figure this out. Look at it section by section. If you look at it all at once, you're going to want to die. Like third period wanted to. Then once I did it, they were like, oh, it was really that easy? Yeah, don't overthink it. You should all already have the answer to part A.
oh, okay.
Honestly, part B.
All right.
So I'm just going to write this out so that we can have room to put down answers as you guys guess them, as you guys get there. But everybody should have part A. If you guys want a hint for part A and B, you really only have to like use that.
Yeah. Yeah, by the way, if you said it's dropping to the final. Yeah, on the first part of it, because she said it's dropping.
Are you sure about that, hon? I think you're very wrong.
Who, me?
I heard her saying it. I think she's very wrong.
What? Zero?
Yeah.
Oh, so then.
Does anybody have an answer on part A yet? Okay, does everybody agree with that? Okay, let's talk about how we got there really quick. What did you do?
1/2 0.4 times 6.
Bam. Okay. For part B, use the same equation. Is it what? I don't know, but I'll put it up here. I'll put it up here until somebody says they agree or disagree.
Yeah.
You got the same thing, Rose? Okay, how do we get there?
Multiply 2 over.
Yeah, we multiply 2 over, then what do we do?
Divide by m.
And
Agree. Yep, I got it.
awesome. Now part C. How do we get the total work? Well, we have, this is a kinetic energy and a kinetic energy, right?
Yeah.
So what's our final kinetic energy? 25 joules. What's our initial kinetic energy? So what is our overall total work that was done? What is it? 17 point what? You guys agree with that? Awesome. We've got one more example to do, then we're done for the day, okay? Listen, there were some people complaining last semester that there weren't enough examples, so I got all the examples. I'm just gonna start erasing over here. I'll slowly make my way. Like I said, we got one more example. Okay, one more example. I guess. So, in this example, we have someone pulling a sled. And as they're pulling the sled, they're going to have done 19 joules of work. The sled is a mass of 6.4 kilograms. And it's going a distance of 2 meters. No other work is done on the sled. Its initial velocity is 5 meters per second. I want to know what its final speed is. So which of these equations do you think we're going to need to use? Good guess. We're going to do work is equal to 1/2 mvf squared minus 1/2 mv naught squared. Okay, what are we trying to find? VF. All right, let's rearrange this together. This is a lot more than we've had to deal with previously. What's the first thing we want to do? Subtract what? You guys said subtract. I don't. Add, what am I adding? Yeah, I'm adding this entire term to both sides. So we'll have W plus 1/2 mv naught squared equals 1/2 mvf squared. Now what do we need to do? Multiply the whole thing by 2, okay? So we're going to say 2 will be multiplied by the whole thing, so we'll put it in parentheses. Okay, what do we do now? Okay, after we divide the m, what do we do? Do we have to do anything else? Just plug it in. Okay. Plug it in and let me know what you get.
I got 30.94.
Okay, we have a guess of 30.94. Does anybody agree with that? You got 6.63?
I got 2.06.
You got what?
I got 2.06.
Now I got 5.56.
None of these are matching my answers.
I got 9.
That's what I got.
That was so close to mine.
2.49 meters per second. Okay, so let's think about how we're typing this into our calculators then. Okay, watch. 2 W plus, I'm just showing you how I would do it if I were you.